Alright, so you're interested in Lagrangian mechanics, and before we dive into the nitty-gritty details, let's take a look at why people were motivated to develop what is essentially this alternate framework for dealing with physics. Now remember that the ultimate goal of physics in general, or at least of mechanics, is that when we have some kind of object, and for simplicity here we'll consider point particles, that are undergoing some kind of physical interaction, we want to understand how these particles actually move as a result of these interactions. And the mathematical way of saying that is we want to understand how the position vector of a given particle evolves with time. And to that end, we can already make a lot of headway using just Newtonian mechanics. And the gem of Newtonian mechanics is really Newton's second law of motion: force equals mass times acceleration. And here we've adopted Newton's dot notation for indicating derivatives with respect to time. And in some sense, F equals ma is really the law of physics. And what I mean by that is that F equals ma allows us to break every mechanics problem into two parts. The first part is figuring out what kinds of forces are acting on our particle of interest. For example, we might have gravitational forces, electrical forces, so on and so forth. The central idea here is that we need to find a way to understand how our physical interactions manifest themselves as forces. And once we've identified all the relevant forces that we need to deal with, the next step is to understand how these forces actually affect the trajectory of our particle, which is where F equals ma comes in, because it allows us to write down an equation of motion, which is really just a fancy term for some kind of a differential equation that our particle trajectory ultimately needs to obey. And in fact, this is enough of a constraint that, as long as you supply initial conditions, solving your equation of motion gives you the particle trajectory. So that's Newtonian physics in a nutshell. And the key takeaway here is that what we really need from any framework of physics, not just Newtonian mechanics, is a way to get to the equations of motion. Once you have a way to represent the state of your system, which in this case is our position vector r of t, we need constraints on how that state is allowed to change over time. And it's these constraints that we then call the laws of physics. Now, in the context of Newtonian mechanics, we use forces to represent the mechanisms behind the physical interactions that ultimately get us to our equations of motion. But in the late 1700s, a mathematician named Lagrange comes along, and he poses a very interesting question. Is there some other framework we can use to get to our equations of motion? Maybe one that doesn't rely on the concept of forces. In order to do this, we'll start with a classic problem from introductory physics: a particle moving in one dimension under the influence of a uniform gravitational field. This lets us write our force as mg, and solving this equation of motion gets us the parabolic trajectory we all know and love. Let's say we launched our particle at time t0 from its initial position x0, and we followed it until some time tf. Since the answer to this problem is already known, whatever new framework we come up with has to be able to recover the same answer. And we'll start by asking, what is it that makes this parabolic trajectory so special? Now, the Newtonian answer to this is that, well, it happens to be the only trajectory that satisfies F equals ma. But if you'll bear with me for a second, let's take a look at, say, the straight line constant velocity path, or maybe the arc that's just a little higher than a parabola, and even this wacky bouncy ball kind of path. And we can ask whether if we can find some other criterion that these dotted trajectories fail to satisfy, but that the parabola does satisfy. Before we can get to Lagrange's answer to this question, we have to define a couple of terms and concepts. First, we're going to define a special quantity called the Lagrangian that we can calculate for a particle at any given time. And it's going to be defined by the particle's kinetic energy minus its potential energy. This is what it would look like for our one-dimensional uniform gravitational field example. Now, say we propose a trajectory q of t, such that it starts at the same place and ends up at the same place as our parabolic trajectory. But in between the initial and final times, it can do whatever it wants. And we'll define the action of a trajectory like this. It'll be the integral of the Lagrangian over time. Keep in mind that this is the Lagrangian for our proposed trajectory, so the values we use for our kinetic and potential energies come from q of t and its time derivative. And going back to our example, if we now calculate the action for each of the possible trajectories, what you'll end up seeing is that the parabola is actually the path that gets you the minimum action. But wait, what if that's it? What if that's the rule? And in fact, this is the alternate framework that Lagrange ended up proposing. But let's take a moment to appreciate how much of a philosophical departure this is from Newtonian mechanics. F equals ma tells us that forces determine how objects accelerate, which is really saying that they determine how the particle's velocity changes from one moment to the next. And since velocity is just the time derivative of position, velocity is telling us how position is changing from one moment to the next. So in the context of Newtonian mechanics, the state of the particle in the very next moment depends on what's happening to it right now. But the Lagrangian formalism instead kind of lets the particle think ahead and consider all the paths it could take before choosing its favorite one. And in the next video, we'll dive into the actual math behind all of this, and most importantly, we'll see how we can use this to get to our equations of motion. See you next time.